Hello, welcome to 9.6, using matrices to solve systems of equations. The first thing I want to talk about is an augmented matrix for a system of equations. So augmented matrix in general just means I take a matrix and I make it bigger. Like that's the basic idea behind that terminology. But an augmented matrix for a system of equations, which is often the way it's used, but it's not the only way it's used, is where we're going to have a 2x2 matrix or 3x3, 4x4, basically a square matrix that's going to be the coefficient matrix. So you take the coefficients of the x's, and that's going to be your first column, and a coefficient of the y's, and that's going to be your second column. And if you have z's, that would be, those coefficients would be your third column. And if you had w, then those coefficients would be your fourth column. You get what I'm saying. Basically, you line up the letters, so x's, y's, z's, w's, and those coefficients become a column. The final column, this is the augmented part, because the coefficient part is always going to be square, and then the last row is going to be the constant on the right side of the equation. So your coefficients, line, and then a column for your constants. So let's look at that for then if I had a 3x3 situation. So this is a system of three equations, three unknowns. So to not confuse myself when I'm writing the matrix, I might want to set this up so that I have my x's lined up and my y's lined up. Because notice this equation doesn't have z in it and this equation doesn't have y in it. So right now they're not quite lined up. So to not confuse myself, I might want to line them up. So I would have x plus y. I'm going to have a blank where z would be. And then 2x, I'm going to have a blank where y would be. And then when I'm making my matrix, these blanks are going to be zeros. So for my x's, I have my coefficients are 3, 1, and 2. So that's my first column. The coefficients of my y's are -1, 1, and 0. So that's going to be my second column. The coefficients of my z's is going to be -1, 0, and -3. And then this final row is the constants on the right side of the equation. So that's 0, 5, 2. So that's an augmented matrix. Basically, you're taking a system of equations and turning it into a matrix. And this can be done with any size system, 4 equations, 4 unknowns, 5 equations, 5 unknowns, doesn't matter. You can turn it into a matrix and you would be able to use the techniques that we're going to learn in this section to solve even the bigger matrices. All right, so I want to talk about, so you can also go from matrix to system. Hopefully that's pretty straightforward. Basically, each row is an equation, and this is coefficient of the x, coefficient of the y, coefficient of the z, answer. So we can go in either direction with this. All right, so let's talk about Gaussian elimination. So back when we did systems of three equations without matrices, right? We just did simple systems of three equations. We did elimination twice to get a 2 by 2, and then we did elimination again to get one of the variables by itself. That system is called Gaussian elimination. Basically, Gaussian elimination just means you're ending up with an equation that's x plus something y plus something z equals, I'm running out of room, but there would be a something here. And then the second equation is y plus something z equals something, and then z equals something, and you're ready to start substituting back in. I know there were a lot of somethings in that sentence, but the point is that you have one equation that you can substitute into that has all three variables in it. You have one equation that only has two, and then you have one that is solved for one of your variables. So essentially, you're ready to start substituting back. You can substitute z into this one to get y. You can substitute y and z into this one to get x. And it's already solved here, is what the idea is. So in matrix form, Gaussian elimination looks like this. So you have x by itself, something in front of y, something in front of c, no x, y by itself, something in front of z, no x, no y, something in front of z. That's this is known as row echelon form, and this is what we want to get after we've done Gaussian elimination. So you take a regular matrix, and then once we've done Gaussian elimination, we want to end up with something that looks like this. So the first thing, and when we're doing this, it's usually going to be an augmented matrix, but they just showed it with a regular 3x3 matrix. So what you have in that last column are going to be your solutions, right? So like what you have down here in the last column of the augmented matrix is going to be z, because this is essentially 1z equals whatever is here. So this will be z, and you can plug that back in and then plug that back in. So that's kind of the idea. So how kind of the game plan of how we're going to do this is you want to get the 1 here, and then this 0, and then this 0, and then this 1, and then this 0, and then this 1. So you're going to get you start in the top left hand corner. You start in the top left hand corner, you get the zeros below that, move down to the next one, the zeros below that, and your 1's are always going to make this diagonal. That's going to be really important. All right, so okay. All right, so let's look at an example with a 2x2 system. So to actually do Gaussian elimination, there are certain things that we're allowed to do to get that form. And they're the same things that we're allowed to do to a regular equation, right? I can multiply a row by a number, I can add rows together, and I can switch rows. So I can switch the order. I haven't changed the meaning of the matrix. For example, if I just wrote this row here and this row here, right? So I can switch rows, which is actually the first thing they do here. I can multiply rows and add rows and subtract, technically, right? I can add and subtract rows, I can multiply rows by a constant, and I can switch rows. Those are the three things that I'm allowed to do. So this notation shows you what they did in each one. So this means they switched row 1 and row 2, which makes sense because they needed a 1 up here in this upper left-hand corner. So it makes sense, since there was already a 1 there, to just go ahead and switch the rows, and then you have that 1, and the next thing we're going to do is we're going to get rid of this 2. So to get rid of the 2, right, we want a 0 here. We're going to multiply the top row, row 1, by -2, and then add the rows together. And then we're going to put it in row 2. That's what this whole form means, right? Multiply -2 by row 1, add the 2 rows together. Sorry, -2. Add the 2 rows together and then put it in row 2. So when we do that, I'm gonna write up here. So to multiply the row run by 2, we're going to get, sorry, by -2, we're going to get -2. I'm just going to write it above our original row 1. +2 and -1, right? Hopefully you can see that. So this would be -2, +2, and -1 if we multiply that by -2. And then we're going to add this new row with this row, and we're going to put it in row 2. So -2 plus 2 is 0, which is exactly what we wanted. The whole reason that we multiplied by -2 was so that we could get this to be 0. 2 plus 3 is 5. -1 plus 6 is 5. So this is our new row 2. Row 1 stayed the same because the only thing we were trying to change was row 2. The next thing we're going to do is we're going to get this to be 1, because remember, we want that diagonal of 1s. So we want this to be 1, so we're just going to divide this row by 5. So we get 0, 1, 1. So you notice they just multiply by 1/5 and put it in R2. So we get that. So this is row echelon form. So all of this that we did was Gaussian elimination. And now we have row echelon form. So what this means is that y equals 1. That's what this tells us, because this is the column for y. So this tells us that y equals 1. And then we can substitute that in here to get x. Alternatively, we can get this to be 0. This is what I'm talking about now is called a reduced row echelon form. We can get this to be 0, and then this side will just give us the answer. We don't have to substitute. So if we got this to be, we could get this to be 0 by actually just adding the 2, right? If I added these 2 together, I would get 0, so I don't have to multiply by anything. So I'm going to go ahead and do that. So what I'm going to do is R1 plus R2 equals R1. In other words, I'm going to add the 2 rows together and I'm going to put it in R1. So 1 plus 0 is 1, -1 plus 1 is 0, and 1/2 plus 1 is 3/2. And then my row 2 stays the same. So this now says x equals 3/2 and y equals 1, and I can read my solution right off of that. So we get the same answer this way as they did by turning it back into equations and substituting back through. So you can do it either way. And again, this is called reduced row echelon form. So what you want is you want a diagonal of 1s and everything else to be 0s. And in the next video, we'll do an example with a 3 by 3 matrix.